It's a pleasure to be back on the conference circus. It's been a while. As many of you had the same experience. It's been a long time without actually going to on-site talks, and this is a super amazing opportunity to actually talk to you about some of the fun stuff that we have been doing. This conference is called NoHat, and I figured we'll actually, as we're riding the fuzzing hype train and trying to figure out if we can find vulnerabilities and use fuzzing to discover different kind of vulnerabilities, we're still wearing some form of hat, right? But can be an arbitrary warm hat as winter is coming, and we'll see what we can do. A little bit about me. I'm an academic, but that shouldn't stop you from listening to me. It just means that I'm giving you tools while you can still find bugs with them. Right, so we've had this discussion a while, and yesterday during dinner, for example, and one of the big differences is if security researchers give talks that are primarily interested in bug bounties, they will only release their tools whenever their tool no longer finds any effective bugs. What we researchers do is we try to get as much fame as possible, and we want to release tools much earlier than others. So we do a proof of concept. We show that a new technique is actually useful. And as researchers or as academics, we have to be poor. So we're not trying to get as much money out of the bug bounty programs as possible, but we're releasing tools so that you folks can actually use them. So all the different things that I'm talking about today are open source. You can download them, you can play with them, you can figure them out, you can integrate them into your tool chains, and you should, right? So just to give you a bit of perspective of what kind of research we're doing, we're working on 3 large areas in my group, and I've got about 20-ish people working on different aspects. We do software testing, we do mitigations, and we do compartments. Compartments is like you have large complex software, you break it into small components, you do fault domains, and you try to figure out that this actually makes your system a bit more secure. Mitigations, I'm sure you know control flow integrity, shadow stacks, and so on. This is also an area that we're dabbling in a bit. But most interesting to you, because you want to make money, is software testing. And software testing is a tool to help the developer to prune bugs, using fuzzing to discover them and sanitization to detect them. Now, that aside, right, we're going to focus on fuzzing and bug finding and turning stuff into exploitable crashes from now on. I've looked around at the last couple of conferences just this year, academic and hacker conferences as well, and all of these top conferences have something in common. Just looking at the program, each of these conferences has like a full session or 2 sessions or 3 sessions on fuzzing. This is Usenix security, this is NDSS, this is, first was SMP, this is Usenix security, and there's RAID. CCS was just last week or this week. It had 2 sessions on fuzzing. So fuzzing is a very hot and ongoing topic. Now, you may wonder why are we doing fuzzing, right? We've just heard from David that we've been doing security for 20, 30 years, right? Why is this still interesting, right? Well, bugs are still everywhere. There's bugs wherever you look at, right? And you just have to poke the software a little bit. It's going to explode in your face and crash. And some of these explosions can actually have some collateral damage and allow the attacker to take over your system. As many bugs are exploitable, right? And this can result in your system being compromised by ransomware, your virtual machine being taken over, your super fancy new electric car being turned into a remotely controlled toy vehicle, which is fun for the hacker on the control. It's not so much fun for you sitting in the car. It can invade your physical spaces by turning smart locks into matching opening devices and so on. Right? Going back to what I said before, there's the difference between software testing and mitigations. We could now put in a lot of effort into mitigation, making the exploitation of these bugs as hard as possible, but this wouldn't help us in removing the bugs from the software, right? It would just make exploitation harder. And you hackers are clever. You will figure out a way to actually get around these mitigations and develop tooling and so on. So it's not going to be super effective. On the other hand, if we actually use software testing to find all these vulnerabilities, we have an opportunity to fix the code and actually make them reduce the exploitability. You may remember from other academics, there's tools like symbolic execution, formal verification, and so on. These are all great if your code size is less than 100 lines of code. Right? If you have a little bit more complex code than that, it's a bit more difficult, right? And last time I checked and looked at our code, for example, the Google Chrome, the browser, there's more than 100 million lines of code that you're running as part of this software stack. There's no way that you can formally verify this. There's no way you can symbolically execute it. And just for reference in code complexity, because like 100 million lines of code is really, really hard to imagine, I have two pictures here. One of them is Margaret Hamilton, who was responsible for the Apollo guidance computer. You're too young for that, but that thing flew to the moon on very primitive hardware. And they printed out the software stack that was running on the system in assembly code. And like, if you're generous, there's about 2 meters of software complexity, right? If we print out the Google source code, we have about 400 meters of complexity in a high-level language. So this is much more complex and much harder to assess. So we need some form of automated techniques to actually handle this massive amount of complexity without it breaking down. David luckily already introduced fuzzing. I'm just going to do it one more time because we saw that a lot of people actually did not work with fuzzing yet. So if you regret not holding up your hand before, I will bore you for 2 minutes about how fuzzing actually works. If you already do fuzzing, bear with me. This is going to get more interesting very, very quickly. So fuzzing in a nutshell, you have a target program, a software under test, as David called it. You run it, you pass it some parameters, you see if it crashes. A simple fuzzer is, while true, you just throw random stuff at it, and you see if you remember if it crashes. And the main goal of fuzzing is, don't be clever, don't spend too many cycles, don't overthink it, be fast. As many executions as possible. We want to know if this input crashes. If the input crashes, we'll set it aside and use it for later analysis. So we have this input, we run the program under test in some kind of virtual environment. We see if it crashes. If it crashes, we store the input, set the input aside, and keep it for later analysis. This helps the developer to actually have a witness of, if you run the program with this input, it's going to crash, and you can use this for debugging to fix and identify the bug. And there's obviously a loop, right? We run the program, we generate new input, we run it again, we run it again. If it crashes, we store it, and we do this until we run out of resources. Now, this is fairly dumb. And this has been like that until 2010-ish, where we just do random changes to the input and hope that we will trigger some more interesting behavior. Now, if we use some form of information about the program, just like a note of which kind of functionality has been executed, we know which inputs that we randomly create trigger some kind of interesting behavior. And then instead of just modifying the root input or the empty input, we can modify the input that already triggered some interesting behavior before. So this is a kind of change in a thought pattern. Instead of just doing it from scratch every single time we create an input, we modify input that has been successful before, hoping that it will be successful again and more interesting again. Right? So to make fuzzing effective, and find more interesting bugs, there's a couple of things we have to look at when we're optimizing. First, our test cases should trigger bugs, so we're using some kind of coverage-guided fuzzing for that. Second, the fuzzer must be able to detect the bugs, right? If it just silently passes the bugs and doesn't really figure out if there's been a bug triggered or not, tough luck, right? And performance is key. Fuzzing is a zero-sum game. Going back to also the introduction that David did using game theory, right? You have a finite amount of resources. Even if you're playing this game for an infinite amount of time, at any point in time, you have a finite amount of resources. And you want to get as many bugs out of the cycles that you have available as possible. So that's what, as an engineer, really, really drives me, right? So I want to get, like, I know I have a cluster of a couple of hundred cores where we can run fuzzing. I want to get as many bugs out of these cores as possible, right? So keep this in mind, that this is an inherent optimization game. Let's focus on the first challenge, tracking coverage. And the current state of the art is gray box-based mutation coverage, or fuzzing based on feedback from simple code coverage that we have. There's a different kind of instrumentations that we can have, and the overarching goal is you take the source code or the binary, you instrument it, and whenever a given code area is executed, you record it on your magic map. There's different kind of coverages that are out there. There's function coverage, block coverage, line coverage, edge coverage, whatnot. And it's an inherent trade-off on how you want to record what areas you have executed. The more cycles you spend on recording coverage, the fewer cycles you're actually spending executing the code. On one hand, you may get better information about what you're executing. On the other hand, it's more costly to collect. So you'll have to figure out some form of trade-off here. And when we're looking at coverage collection, the fuzzer keeps, like as the fuzzer is running, it keeps track of what kind of code areas have been executed, what kind of functionalities have been triggered. And the fuzzer keeps this as part of some form of global coverage, right? And it's like a map of which edge has been executed as many times as in my example here, right? And then for each execution, the fuzzer keeps a local map, and if the collected coverage is higher for the topmost bit, then the global coverage will update the global coverage and set the seed aside for further mutation. Right, so the fuzzer has created this one input, we execute it, we check the collected coverage. Yeah, sure, we've executed a couple of edges more times. So for example, the orange edge and the pink edge has been executed more times, but we haven't increased enough. Right, so the highest most bit is not gonna change, so we're gonna just keep it the same. Let's do one more input. Here now the pink bit has changed. The pink counter has changed from 7 to 8, so we've executed this loop more times. We've gone through the loop on the right-hand side in this control flow graph more times. This is higher than the topmost bit that we have stored so far. Therefore, this is considered an interesting new seed. Therefore, the fuzzer will set it aside and continue fuzzing with it. Right? We'll store this and then figure out what to do and how to continue with it. So fuzzing has been rather boring until 2011, 12-ish, until AFL actually came along. And there's been two events that happened. On one hand, there was the Cyber Grand Challenge that kind of kicked off a lot of this research. Who knows the Cyber Grand Challenge? Okay, so this was one of the DARPA Grand Challenges. DARPA, the US Defense Agency, they kind of pose these large challenges out there to humanity, and there's researchers try to find a way to solve it. And the Cyber Grand Challenge was figuring out a way to automatically find vulnerabilities and then exploit them in some way. There's been grand challenges for autonomous driving and location, geolocation, and so on, and a bunch of others. And this challenge was focused on vulnerability search and vulnerability discovery. And this led to what I call the Cambrian explosion of fuzzers. If you've paid attention in biology, the Cambrian explosion is when life happened and it just exploded and there's all these life forms that came out. And we see the same with all the fuzzers. There's now hundreds of fuzzers at each conference. There's 10 new fuzzers being proposed, and all with slight differences and deviations. So we've been working on actually trying to categorize, systematize all these differences to help other researchers also figuring out how they relate to each other and what they belong to, both on the control flow coverage edge, but also on the data flow coverage edge. So this will help you choose what kind of fuzzer you want to have, and also gives you a way to measure for a given program what kind of feedback will be most useful. So it's a summary for tracking coverage. Coverage helps a fuzzer to effectively explore new code areas. It's a feedback process that tells the fuzzer what areas actually are interesting. Code coverage and edge coverage, but for example, is very cheap to obtain. It's like 2 or 3% overhead and precise enough in general. So all the fuzzers pretty much rely on a form of code coverage. There's many flavors of code coverage with subtle differences. Do check out, and you may want to hand tune, but it's very easy to just set up a fuzzer, go with it, and then tune along while you actually observe your fuzzing campaign. Future research, so if you are interested in writing new, more interesting fuzzers, alternatives to code coverage. What is a good approximation of code coverage? For example, in areas where you cannot really instrument your binary, think of embedded systems, think of systems where you don't have debug primitives or like closed environments or other kind of binaries that make it hard for you to obtain this information. Combining different coverages and also adjusting coverage as needed during the campaign. For example, after you finish the exploration campaign and you know how code actually works, you want to go into an exploitation phase where you figure out individual bugs, and there some more fine-grained feedback may actually be fairly useful. Second challenge, detecting bugs. Well, if we would just know that a bug is there, this would be super easy, right? If the bug would just tell you, hey, this is the bug, I'm on line 15, fifth character, go fix me, right? Unfortunately, this doesn't work that way, and we need some form of oracle. We need a way that tells us that, hey, there actually is a bug. If you don't have source code, you may just YOLO it, or you could statically rewrite the binary, right? Something that you get, like if your program seg faults, yeah, that's very likely a bug, right? So that's a very cheap oracle, if it seg faults or not. You can statically rewrite the binary to make it more likely to seg fault, to retrofit some kind of fuzzing or address sanitization instrumentation into it, and we'll talk about this in a bit. Or if you do have source code, that's the ideal case. And I disagree a little bit with David here, and I didn't pose a question, so you cannot really shoot me down, and I can just, as a speaker now, I can talk about it, that often if you do have source code, it makes fuzzing and bug finding much easier, and you can actually spend some cycles on instrumenting it with different kind of sanitizers. Who knows sanitizers? Quick show of hands. Very few. The cheapest way to find bugs, as I tell my students, is sanitizers. Yes, hand sanitizer. Everybody knows hand sanitizers, right? It gets rid of germs on your hands, especially over the last two years, right? A sanitizer is the cheapest way when you're writing code to find vulnerabilities in your code. You do dash f sanitize equals address. Your code compiles, and if you touch illegal memory, you get a nice bug report that tells you, hey, there's a bug over here. You should during testing, you should always compile your code with sanitization. There's concurrency sanitizers, or thread sanitizers. There's type sanitizers. Logic bugs, we don't really have something useful for logic bugs yet. So that's a nice way for you to look at future research. But I don't just want to talk about sanitizers because this research has already been done. You should be using sanitization during fuzzing. And we can talk about some of the trade-offs here, but I'm happy to do that during the break. But the main goal or the main issue I want to talk about is that, yes, crashes are great, but having actual bugs are much better. A fuzzing campaign produces n crashing seeds that map to m bugs, right? So after fuzzing, you have n crashing seeds, and your fuzzer tells you all of these seeds are unique bugs, right? But you don't know. In essence, there's only going to be m actual bugs, and often m is much smaller than n, right? So now, given that you have these 7,000 total crashes or 1,000 unique crashes, how do you distill them into the number of unique bugs? Right, in this example here, there were 7,000 crashes on AFL, 124 unique, and all of them were the same bug. Right, you've got a couple of overhead, a couple of orders of magnitude difference between the number of real bugs and the unique bugs that your fuzzer reports. And this is going to cost you a lot of resources. And if you're a bug bounty hunter, you're only paid once per bug, right? So it doesn't matter if you say, hey, there's more bugs here, right? It just doesn't work like that. Now, the challenge that we have is, given n, the number of crashing seeds, how do we distill them into the set of actual bugs? Well, one approach is we could just do call stacks, right? Group all the crashes based on the hash of top k frames. Well, the issue here is that there's a whole bunch of type 1 errors. So there's going to be duplicate bugs that crash at different addresses, and we'll lose those. We'll overcount by about 2 orders of magnitude. Crash location, that's another simple estimator. So we just record the crash location and treat each crash location as a different bug. The prime counter example here are use after 3 bugs. Use after 3 bugs will crash anywhere, right? So the crash location has nothing to do with the actual bug that you're looking at. So this is pretty useless as well, unfortunately. So both of these approaches overcount by 2 to 3 orders of magnitude, wasting your developer time. So if for 100 potential bugs, you spend 100 days analyzing them, and then you have one final bug. That's not going to be super worthwhile. So we spent some resources. We did 79 CPU years of fuzzing, and we looked at 254,000 crashing seeds that we got out of it. That's actually a fairly substantial number. And then we analyzed the different seeds. It's actually great if you have PhD students. They can actually do a lot of stuff and look at this manually, so you can get ground truth. And the existing grouping that have been used, both over and under approximate bugs. This is bad. Each bug is triggerable by a unique trigger, right? Like if you think about it, each bug that is out there will have some form of unique trigger that you can use to actually trigger the bug. And large sections, if you trace the program execution to the bug, large sections of this execution path are irrelevant to the crash. Now, if we could identify the small sequence of the path that is actually responsible for the vulnerability and for the crash, we could use this to identify it based on the topology. So our idea that we had is we want to minimize the path, prune all the irrelevant sections that do not correspond to the bug trigger, and then cluster by graph topology to match similar kind of subpaths. And we're introducing Igor for that. Igors are, if you know Discworld, and I'm a huge fan of the Discworld novels. You should totally read them. In Ankh-Morpork, there's a group of Igors that are helpful servants to crazy scientists. And we used the name for that. It's Terry Pratchett is the author, and you should all read his books. They're amazing. So we're introducing Igor to help us distill all these different crashes, and the underlying pipeline looks like that. We get all the crashes in, we do some data processing, filtering, and then Igor fuzzing, and then we do graph clustering, and then we get clustered crashes. So for each of the bugs, we get a cluster of the crashes out there. You see fuzzing in the first box. I'm going to spend some more time on this fuzzing. We're going to do fuzzing, but different, right? So the goal of fuzzing usually is we want to maximize coverage. We want to trigger new and different bugs. For Igor fuzz, we don't. Now with Igor fuzz, we flipped the fitness function, and we want to have as little coverage as possible while triggering the same bug. Original fuzzing is we want to get more coverage and hit different locations. What we do is, given a seed, we want to hit less coverage and the same crash. And this allows us to shrink and prune all of the code that is not necessary. Like imagine you spending hours and days trying to get rid of functionality that is not bug relevant. This is using a machine that does that, right? So it gets rid of all the nodes here on the right-hand side. That's a libpng example that we triaged. You see all the basic blocks. The red ones are those that have been pruned, and the green ones are those that have been added to make the path simpler and making the execution much more efficient, right? This allows us to get rid of large chunks of the path and figuring out the details. We then do clustering for the different bugs. Before our coverage decrease fuzzing, clustering was a bit of a shit show. As you see on the left-hand side, it was very hard to distinguish these different crashes. Afterwards, on the right-hand side, you see distinct clusters for all the different CVs. So it is very effective at grouping crashes into small groups. And this gives you a way of clustering 250,000 crashes that we had into 40 bugs. So the summary for Igor is fuzzing is great at producing crashes when using the right sanitizer, of course, but programmers are just overwhelmed by the thousands of crashes that we have. We can minimize the pass lengths of seeds to enable this similarity matching. And using our tool, we grouped these 254,000 crashes into 39 unique bugs and 48 clusters. So it's much easier for you to analyze 48 clusters than 254,000 seeds, I would say. So check out the paper. The source is online. We are currently working on a tutorial and making it more usable for analysts. Many of you are working on fuzzers, about 2 to 5% according to show of hands, but I would guess much more because it's very hard for you to show hands. But if you're developing a new fuzzer for an area, right, you may not want to open source it or whatnot, but you want to figure out, is my fuzzer better than the fuzzer that already exists, right? Is it worthwhile to invest my time into tuning the strategy? So you want to find some kind of metrics to compare your fuzzer to other fuzzers. It could be code coverage, it could be crashes, it could be bugs. Well, code coverage is subjective. It's very hard to measure. Talk to me about this during the coffee break. Crashes are imprecise, as we've just seen. And for bugs, you lack ground truth, right? You don't really know how many bugs will be in the code. So what we did is we created a benchmark using real software that allows you to test all these different fuzzers, including your fuzzer. It's very easy to set up, and then you can evaluate if your fuzzer is actually better than other fuzzers. That just as a side note, if you want to check it out, it's called Magma, and it contains real-world software that you can use to drive your fuzzering code. Two quick notes on some fuzzing niches and techniques I want to mention in some neat areas, especially as the discussion came up today, this morning, and yesterday during the dinner. One of the areas where fuzzing is really hard are embedded systems. And with embedded systems, I'm thinking about like these small little embedded systems where you run firmware and you have some ARM Cortex M0, M4, or some other kind of constrained environment. And the issue there is, right, they're not running an operating system. They're running on the hardware itself. They are heavily customized. It's very hard to use. It's very hard to look at. The firmware is task dependent. There's a metric shit ton of different peripherals you would have to support, and it's super hard, right? There's no way for you to do peripheral discovery and to actually support all these different systems. One thing all of these systems have in common, though, is that they have some form of HAL, a hardware abstraction layer. And there's a bunch of different HALs, and we use this. So instead of implementing an emulator for each individual peripheral, we implement an abstraction layer that allows you to hook when an individual HAL function was called. Like whenever a HAL function is called, for example, UART read or UART write, instead of implementing and emulating the UART chip, which would drive us insane, we allow you to intercept and then replace it with a 5-line Python script. So our hallucinator replaces the underlying HALs and other libraries with high-level implementations and gives you as the developer, the analyst, the opportunity to implement these high-level abstractions. So this transforms the rehosting problem of rehosting and re-implementing all these different peripherals and supporting tens of thousands of devices into supporting a dozen of HAL. And this is much easier. If you're looking at a modern firmware on such an embedded system, we have the off-chip hardware, we have on-chip hardware, and you have the firmware running on top of it. If you peek into the firmware a bit, right, we've got the vendor HAL, the platform HAL, and a bunch of other abstraction layers. On top of that, we may have RTOS, protocol stacks such as low-level IP, SIGBee, peripheral libraries like sensors and so on, and then the application code on top. Our rehosting uses QEMU to run all the low-level instructions, and then it finds interception points for whenever hardware is accessed through the HAL, and you can then implement these HAL abstractions on top of it. Either running the full stack, application code, RTOS, the real-time operating system protocol stacks, or even going higher and abstracting these low-level systems as well, giving you an opportunity to intersect and intercept the application code. So in Hallucinator, we do HAL-based firmware rehosting, And you can locate health functions in firmware in the firmware address space and then use this as individual hooks. QEMU translates the instructions. We trap on peripheral access based on the health functions and then enable fine-grained introspection. We just did a tutorial for the folks at ONR. The tutorial is online on the website using the different slides and so on as well. So you can play through the tutorial and do some re-hosting of your firmware as you're playing with it. This is also great for firmware fuzzing if you're into that kind of thing. A second project I want to talk about that we've been pushing really hard on, also making it available to you folks, is RetroWrite. It's a tool that allows you to statically rewrite existing binary code for both x86 and AArch64. So you start with an ELF binary that can be stripped. You do symbolization, so you recover all the different offsets and the different code layouts, resulting in the form of labeled assembly. And then you can run a bunch of instrumentation passes on top of this reassembled code. Memory sanitization, address sanitization, fuzzing coverage, or control flow integrity, and then you compile it back down. Features that RetroWrite already has, it's a zero overhead rewriter for AArch64 and x64. So it gives you a way to rewrite your binaries at very high speed and very high compatibility. Fully symbolizes ARM and x64 code, and we provide, as I said, address sanitization, fuzzing, and coverage, function shuffling, exception handling, basic control flow integrity, and shadow stacks. We've got a tutorial on here as well. The C++ support is very iffy at the moment because C++ exceptions are hard, but we're working on that. If you're interested in using it, the x86 version is fairly stable. The ARM version is coming along. If you're interested in the ARM version, please reach out. We give early developer access, so we would be very interested in working with you on that. I want to spend the last couple of minutes in talking about some of the unsolved challenges that I see in fuzzing, and also give you an opportunity to, later during coffee, hit me up and talk about all of these different things, and we'll be very interested in discussing those. And if you have solutions, please let me know. These are very interesting and active areas of research. First off, metrics for starting seeds, right? We often have it that you have fuzzed a software before. Now you have 40,000 seeds. You've seen that you want to continue fuzzing because the software changed a bit or the configuration changed a bit. Which of these 40,000 seeds do you use as your starting corpus? How do you generate good starting corpora, right? Like in academia, papers are often evaluated with start with empty seeds. But any good analyst will spend 10 minutes to create a set of good starting seeds and then use those to actually jumpstart the exploration and fuzzing process. Cross-distillation to reuse seeds among targets. We've had great success when we did USB kernel fuzzing, where we found around 40 O-days in the Linux kernel, where we fuzzed a USB target, and then the seeds that we got from there, we just replayed on Windows and Mac OS, and then found a couple of O-days in Windows and Mac OS as well, with incomplete USB parsing. So this is an interesting way to do cross-distillation between targets, and it goes back to a bit to what David said with the A/B testing with the different URL libs. Stateful programs and network protocols. This is a really hard target to look at. Handling more peripherals, helping developers analyze discovered crashes, and distinguishing the exploration phase from the exploitation phase during fuzzing. And I think we need to break this into multiple phases where we are using different kinds of feedback, different kind of mutators, different kind of options there. Talk to me about this during the break or anytime during the day. I'll be around. Let me conclude. Please join me in riding the fuzzing hype train. It's an amazing train. Bugs are everywhere, and fuzzers allow you to find these bugs to then do fun stuff with them. It's easily integratable into the development chain. As an analyst, you can use it to target bug bounty programs. The goal is that you leverage feedback from coverage to find more and interesting crashes. And best feedback and mutations are program dependent. So we'll start or slowly move to an area where we will hand tune the fuzzers to the different use cases. Some interesting future research that you could look at, increasing usability, reducing startup costs. That's also something that we are looking at. We're providing the tutorials on the websites and so on. Specializing fuzzing for new environments, such as embedded systems, and then helping developers make sense of the bugs. This is what the Igor system, for example, was targeting at. That's all what I wanted to say today. I hope we have some time for questions. Thank you for your attention, and please.